Welcome to SSI Meetup. Today we have with us Sam Smith, which is one of the guys who has been very early on in the whole SSI space, even before it became SSI in itself, and he was involved with the precursor of what Sovereign became and collaborated with Evanim, has his own company with Digital Trust Ventures, and also is a freelancer and does contractor jobs with Prosapien. Very active in the SSI space and doing a lot of interesting stuff. And he will be telling us much more today about decentralized key management. And that's a key aspect or key subject because, as all of you know, if you want to make a real, truly decentralized SSI ecosystem, that's one of the key aspects that needs to happen if we really want to achieve that. So very happy to have Sam with us today. We're going to go briefly to the next slide to tell you what SSI Meetup is about for those of you that never joined us before. So SSI Meetup is basically an initiative that we started 2 years ago that is open to everyone who's interested in SSI. It doesn't matter what you do or where you are, if you're a company, an individual, or an association, and all the content we share here is shared with the Creative Commons by share alike license, which basically means it's open source and you can reuse all the material that is being published here. Only thing you have to do, please give credit back to the creator of the content. Today, please give credit back to Sam Smith if you reuse his content, and of course also to SSI Meetup. Everything will be uploaded, the video recording of this presentation, the slideshare presentation, and the Google slide deck itself will be available too, so you can download it and use it. A lot of people are doing this all over the world. If you have any questions during the presentation, please bring them up using the question tool, and I'll share those questions with Sam during the presentation or at the end of the presentation. And yeah, and that's the main technical stuff we have to cover. And the next thing is to go into the really interesting stuff that Sam has to share with us today. Sam, welcome so much to SSI Meetup.
Oh, thank you, Alex. It's great to be here. And just a couple of slides so that people don't have to write all this stuff down, but when you go back and look at the slide deck, there's links here for resources associated with KERI, which stands for Key Event Receipt Infrastructure. There's a white paper that goes into great depth, and so you can read the white paper here or here and research that. Here's some background references of papers that are related to the sort of core idea, which comes from something called a self-certifying identifier. You can look at those. They're also referenced in the paper. And so I'm just going to give a brief introduction to the idea behind KERI and why KERI takes the approach that it does to identity. As humans, there is what we call a human basis of trust, how we interact with people and how we trust them. And in person, we have developed the ability to trust other people because we can know them in person. We can recognize them. We know who they are, and therefore we have a basis of trusting them. But on the internet, we can't really know somebody because all we see on the internet are bits transmitted over the internet. So we really can't trust anyone because we don't know, we just know bits. And so we need to replace the human basis of trust with the cryptographic root of trust. And that's the core of KERI and key management and identifiers and everything that we want to do with decentralized identity and self-sovereign identity, is that we have to start with something. We have to start with the root of trust. And that root of trust is based on verifiable digital signatures using asymmetric key cryptography, which that means is that we can't trust, or may not trust in what was said, but we may trust in who said it, and that who is the controller of a private key from a public-private key pair. So we can digitally sign something, and we know that the controller of the private key made the statement, but we don't know that the statement itself was valid in any way. We just know that we can make attribution to the controller of the private key. And so the root of trust is consistent attribution via non-reputable statements from the digital signatures. That's all we have to start with. We don't have anything better than that. That's all crypto gives us. But if we are able to maintain that consistent attribution over time via histories of these statements, then we can build trust in a reputation about what was said. And so people often confuse trust when they talk about trust and cryptography and identity systems, and they miss this connection that you really only, cryptography only gives you trust in that somebody that controlled a private key made a statement, and everything else comes from consistent attribution to those statements. And so where that leads us is to, how do we fix the internet? The internet protocol is broken because it has no security layer. When it was designed, it left out the 2 layers in the 7-layer OSI model where you have security. The session layer is authentication. Now, had they put one in there, it probably would be a bad form of authentication because 30 years ago, crypto wasn't as good as it is now. But that said, what has happened is that instead of having a standard security layer that everybody uses for the internet protocol, we have bolt-on identity system security overlays. And the prime example is the domain name system certificate authority system that everybody uses in the web. What that means is that security on the internet comes through some form of an identity system security overlay. So what we want to do is establish the authenticity of an IP packets message payload. And the reason we want to do that is that internet protocol, anybody can forge the source in an IP packet. So you don't know who sent the packet, because anybody can forge that. Anything along the path can substitute and forge the packet. So you have to add some sort of authenticity or authentication to the packet. So the standard approach for, and this is using pretty much every identity system security overlay that is used for the internet, is that you have a mapping. The identity system provides a mapping between a cryptographic key pair and an identifier, and then the message itself includes this identifier, the data, and then a signature using the key pair that you can then verify to determine if the message is authentic. The security of this approach is contingent on the security of the mapping between the key pair and the identifier. What that means is that when you issue an identifier, you're making 3 bindings. You're binding a controller to a key pair, you're binding a key pair to an identifier, and you're binding a controller to the identifier. Because you're basically saying this controller is associated with this identifier and controls this identifier through this key pair. And if any of those bindings are weak, then you have a security vulnerability. So let's look at how administrative identifier issuance and binding works. And this is the way, and this is the pattern that almost every administrative identity system that we would have been exposed to uses. And so I've simplified and generalized it, but it is the pattern that is generally applicable. You have entropy, cryptographic entropy. The controller captures that, generates a key pair, and then an administrator of the identifier makes an assertion that binds the key pair to the identifier. So this might be a certificate, as in a certificate authority is the administrator, and it creates a certificate that binds the key pair to identifier, and then you can verify that identifier against the administrator based on their certification. What it means now is that in this issuance process, you have a strong binding between the controller and the key pair, because the controller is the only entity on the planet that can capture that energy and generate the key pair. So the strength of that binding is the public-private key system that you're using. But the binding between the key pair and the identifier is weak, because it's just an assertion made by an administrator. And if you can hack or compromise that assertion, then you can replace that binding with a different binding. And so the pattern is an example of DNS hijacking. So there was a spate of thousands of DNS domains that were hijacked in 2019 and continue to say, because people haven't in general fixed their systems, that basically where someone goes in and either hacks a DNS provider or hacks a registrar of a name server record, and then is able to convince Let's Encrypt some other certificate provider to issue a valid certificate against that domain name with a key pair, but the key pair is controlled by the hacker, not by the actual controller of the identity. So they basically hijacked the administrative of that binding, and that pattern exists, throughout the identity space. A similar pattern for SIM jacking of your phone. Anytime you have an identifier where the binding between the key pair and the identifier is asserted by an administrator or administrative entity, the security is dependent on the infrastructure of that administrator policies, how the administrator runs their system, and those are all subject to various types of exploit. So what that means is that when you're building identity systems, you have a secure identity overlay that's based on some trust basis, and in most cases, it's some form of infrastructure. And then based on that overlay, you have a trust domain of interactions that can mutually interact in a trusted way because they all share the same identity overlay and the same trust basis. And so that gives rise to the modern idea of security on the internet. A related concept is the concept of a spanning layer. So when people looked at the dominance of the IP protocol, so back in the 70s and 80s, it wasn't clear that IP was going to dominate. But now everybody's recognized it's the dominant protocol. And one of the things that led to its dominance is the structure, where it had a very thin spanning layer, which is the IP layer, that spanned all of the supporting protocols beneath it and spanned all of the applications that use it above, so that anybody writing an application doesn't need to see anything below the IP layer. They just can address the IP layer. And anybody below the IP layer doesn't need to see the applications above. They can just, use the IP layer. And so that's a very powerful construct that has led to the current shape of the internet. And the term for it is the hourglass shape. There's a narrow waist, which is the IP layer. And there's a theorem called the hourglass theorem that talks about why that is the case to design systems to have a spanning layer. So the problem is that the current IP spanning layer doesn't have a trust layer that is also a spanning layer. And since IP doesn't have security built into it, a trust spanning layer has to be at some higher layer in the stack. And so what we have now is what I call platform lock trust, where if you look, we have a platform, say Facebook, that provides an identity system. So they have a trust overlay that allows applications that run within their domain to be trusted, but they're now locked to their particular trust overlay. And you have Google, any number of blockchains that have identity systems built on top of them have the same architecture, where you've got these walled garden trust domains that are based on a given trust overlay for them. So that is a problem, because now we have trust domain-based segmentation of the internet. So that's what leads to the idea that the internet is broken, because we don't have interoperability, we don't have trustable interoperability. It's highly segmented. So we want to fix that. We don't want to have a bifurcated internet trust map. We want to have a single internet trust map. And to do that, we need to add a trust spanning layer. That means that we're going to add a neck. So we have a waist that is the IP spanning layer. We want to add a trust spanning layer, and it has to be at some higher layer because of the extra work that you have to do to have a secure overlay. But if we can add that trust spanning layer, then we can get rid of the silos in trust and have global interoperability across the internet. So that's a very ambitious idea, but that is the motivation for KERI, is to be able to eventually reach the point where we have a universal trust spanning layer for the internet. And that's why the title is, a secure identity overlay identifier overlay for the internet, to give us that spanning layer. So how do we do that? So how we do that is we start with a root of trust that is truly decentralized. and that is a self-certifying identifier. So if I have a self-certifying identifier, this is what my issuance looks like. A controller, an entity, captures entropy, generates a key pair. The controller also derives the identifier from the key pair, which makes the binding between the key pair and the identifier strong. And that also makes the identifier self-certifying. So the controller becomes the certificate authority for its own identifier. The controller doesn't need to refer or defer to any other entity or any other infrastructure, because the controller itself created the key pair, the identifier, and all the bindings. And so the root of trust is fully cryptographic. There's no infrastructure associated with it. And so if we start there, then we can build a secure system on top of that. And that's the key insight. So what that means is if we start with the self-certifying identifier, then we have strong bindings between the controller, key pair, and identifier. So it fixes the main weakness of any administrative issued identifier, which is the administrator asserting the binding between the key pair and the identifier, and between the controller and the identifier. Those are all cryptographically strong bindings. So let's look at a basic self-certifying identifier. A basic identifier derivation process looks like this. You collect entropy in a random seed, you stretch it, which is a cryptographic one-way function. And the definition of a cryptographic one-way function is a function which is easy to commute in one direction and impossible or practically impossible to compute in the other. So a random seed stretch, usually using some sort of cryptographic hash, is an example of a one-way function. A private key, public key generation function, like an elliptic curve cryptography ED25519 or an EC DSA SecP 256K1, are examples of one-way key generation functions that are practically impossible to invert through brute force, but easy to generate in one direction. Then you attach a code for the derivation, and that generates what I call an identifier prefix. The identifier prefix is your root identifier that you've derived, and it is cryptographically bound to the public key because of the derivation process. Because in this case, the prefix includes the public key explicitly. And so you have a prefix that consists of a derivation code and a public key. You have an inception statement, which has information about the identifier that is signed with the public key. And so that is a very basic self-certifying identifier root of trust. A more sophisticated one is a self-addressing self-certifying identifier. And in this case, you get to the public key and its derivation, and then you add your inception configuration, and then compute a digest of the concatenation of those two, add a derivation that tells you that you did a digest, and now you have a prefix that not only strongly binds to the public key, but now strongly binds to your inception configuration. What this allows you to do now is you can include in your inception configuration any infrastructure that you want to make a part of your identity system. So now the infrastructure is bound to the identifier. And then you can extend this to be multi-signature to get even more security in terms of your signing scheme, or delegation. And I won't go into detail, but if we want to delegate identifiers so that you can horizontally scale your identifier system, so you can have a root identifier that manages a bunch of other delegated identifiers, and so the delegated identifiers can be strongly bound to the root identifier, so that you have a cryptographically derived strong binding all the way through your infrastructure, not dependent on any administration at all. It's all cryptographic. And then you can do a self-signing identifier, so that you actually, the identifier includes the signature, which may be useful in some applications in like a content addressable database, where you're using the signature as your content addressable hash, so you don't have to attach a separate signature, so it may be more efficient to do it that way. So a lot of people are familiar with ledger registration, and I want to spend a little bit of time to contrast self-certifying identifiers with ledger-registered identifiers. And a ledger, in this case, I'm referring to a blockchain like Ethereum or Bitcoin or Sovereign or some other identity totally ordered distributed consensus ledger. In ledger registration, you have two identifiers. The first identifier is an access identifier that allows you to access the ledger. And so the access identifier is usually self-certifying. So on Ethereum, your self-certifying identifier is your Ethereum address. It's just the public key of your, well, it's derived from the public key of your public-private key pair, right? It's a fingerprint of the public key. And since you create the public-private key pair, the individual that creates the address, then it's their identifier. And if they're the first ones to use it, then they have access to Ethereum using that access identifier. But then if you want to register an identifier on say a ledger, then you're going to have a registered identifier. So the ledger transaction is validated given the access identifier and the access key pair signature, and then you create a transaction that in the transaction is a registered identifier, and it includes a binding to a registered key pair and the registration key pair signature. And so now the root of trust in the registered identifier is the ledger transaction, not the cryptographic root of trust that the access identifier is using. So even though the registered identifier may appear to be self-certifying, its root of trust is the ledger transaction. What that results in is that the ledger is now locked. The identifier is now locked to that ledger. And so we don't want to have ledger locked identifiers. We want the identifiers to be portable across ledgers. And so we don't want to use registration as the root of trust. We want to be self-certified all the way. And so the term I use to refer to truly self-certifying identifier systems is autonomic identifier. And the reason I use that is that self-certifying identity has been used and applied to identifier systems that are actually not self-certifying, but they use the term self-sovereign identity being used for identifiers that are not self-certifying. And so this just gives me a way of precisely saying that if it's an autonomic identifier, it is self-certifying and self-sovereign. And autonomic means self-governing, which is the same term as self-sovereign. So an autonomic identifier is not just self-certifying, it's also self-administering because the controller is the administrator for its own identifier. And that makes them portable and truly self-sovereign. So that's the basis. And then this prefix now can be used in a universal identifier by adding namespacing to it. So a W3C DID, if using a self-certifying autonomic identifier for the prefix, could be a form of an autonomic identifier. And that lends to what I call an autonomic identity system. And in an identity system, there's some questions that you need to ask and answer in the identity system design. So you have the why, how, of who controls what, when, and how, right? So the first thing is the root of trust, and we've talked about that. The root of trust is a cryptographic autonomic identifier, right? So that answers the why and the how of who controls the identifier. The source of truth is the controller of the private key, right? So that's the who, and we can bind that to the root of trust. And then the final one is what I call the loci of control, which is what you're controlling, and you're controlling authoritative operations. And so you can verify all the authoritative operations by signing with the key pair that is cryptographically bound to the identifier. And so there's no place that anybody can intervene in the establishment of the authenticity of a control operation, because you can verify it all the way back to the root of trust. So in doing a systems design for an identity system, you have a bunch of different things that you can trade off. So I have a diagram here of the system design trade space and different features that you can leverage from blockchains and cryptography to get different features. And one of the things in designing KERI is I realized that if I wanted portability, I needed to not use some features that constrain me. So, but I don't need total ordering because the controller is the only one that can order events, the controller of the key pair. So I don't need total ordering. I don't need a cryptocurrency to do an identity system. I can use some other cryptocurrency for payment. It doesn't have to be embedded in the identity system. I don't need shared control because the controller is the only controller. So I can avoid that, and I don't need to be locked to a ledger. And so given that I take those out, I can come up with a system that has these features that is an identity system. So it's a matter of trading off different things and composing in a different way. So let's look at KERI specifically. KERI stands for Key Event Receipt Infrastructure. So it starts with key events. And a key event is basically a data structure that has a header, some configuration information, and signatures. So it is an authenticated payload that you can send, and if those signatures are generated by a self-certifying identifier, then it's verifiable. And the events are chained together. So you could say that KERI uses a blockchain, but understand it uses the blockchain in the very narrowest textbook sense, which is a hash chain data structure, not a blockchain in the sense of a totally ordering distributed consensus ledger with a node pool and a proof of work or a proof of stake or a PBFT algorithm. It's a chain in the sense that a controller composes messages and hash chains them together. And so you now have a hash chain data structure that can be verified by anybody who's given a copy of that hash chain data structure. And so that's the core of KERI. There are two types of events. There are establishment events, which establish control authority. So control authority is what are the authoritative key pair at any point in time. For a trivial system, there's one authoritative key pair and it never changes. But if I want persistence in my identifier and I want to be able to survive compromise of my keys, then I need to be able to do things like rotate keys. So in KERI, we have two establishment events. One is an inception event, which is the first event that establishes the identifier. And then we can have any number of rotation events that allow us to change the authoritative public keys. So we start with a root of trust in a public key pair that's bound to the identifier, and then we can rotate authoritatively to other key pairs given signed rotation messages. So the infrastructure that we need is infrastructure that keeps track of those rotations, or key event receipts, which are signed key events infrastructure. So that's where the term KERI comes from, is keeping track of these establishment events. The other type of event, and so we have an establishment subsequence of an inception event and any number of rotation events. There's also non-establishment events. The purpose of a non-establishment event is to be able to do something with the identifier. And primarily what a non-establishment event is that it anchors data to the key event sequence so that you can do things like issue a verifiable credential or revoke a verifiable credential or engage in a transaction where you make a commitment of some form to some other entity, and you can anchor that commitment or that credential issuance to the key event receipt log, so that anybody can verify it. So what you get is a full sequence of events that consist of the establishment subsequence and then interaction events that anchor other things. And the key thing here is, the key thing here is that given the event log, I can establish for each interaction event and anything anchored in that interaction event, the control authority over that event, because it's in the log, and by replaying the log, I know what keys were authoritative at any point in time. So I don't need any intervening infrastructure to make the establishment. I just need to produce a copy of this sequence, and anybody can verify it, and that's the term, when we use the term end-verifiable. So the anchors we call seals because the definition of seal means evidence of authenticity. So anything that's anchored now provides evidence of authenticity of whatever is anchored. And so the three types of seals are a digest of data, a Merkle tree root or hash tree root, or an event seal, which is anchoring an event in some other key event log to a particular location, this key event log, which is primarily used for delegation. But this way we can anchor arbitrary data and provide proof of control authority for that data at the location of the anchoring event. The seals make KERI privacy preserving and data semantic agnostic, because all we're putting on KERI are digests. We're not putting anything else. So if you want to know what the data that is anchored means, whoever created the data can produce that off-chain. There's no on-chain disclosure or correlation of the data other than the digest. So that gives us the ability to be context independent, extensible, which is the goal of KERI, which is to be universal and not tied to any particular data schema. So we get interoperability with respect to establishing control authority totally, but we're using the minimally sufficient means to get there. And so that's an important design feature of KERI. So now we want to talk about the security of a KERI log. If we never rotate keys, then we're good. We don't have to do anything. But if we're going to rotate keys, then we need to track that and establish the security of that. So in KERI we use a couple of terms, and the terms are inconsistency and duplicity. So the dictionary definition of inconsistency is lacking agreement as two or more things in relation to each other. So if I make an inconsistent statement, it means I made a statement about something and made another statement that didn't agree to the first statement. And because all the statements are signed, then they're provably inconsistent. Duplicity is acting in two different ways to two different people concerning the same matter. So I can make inconsistent statements to two different people, but they're not duplicitous. I'd have to make inconsistent statements of the same thing to two different people, and then they would compare notes, and then they would go, oh, you told me one thing, you told him another thing, you're being duplicitous. And so that's what duplicity is. And so what that allows us to do is distinguish between internal and external inconsistency. Internal inconsistent log is not verifiable by the construction of the log being a hash chain data structure. So if I put something in a log and it's inconsistent, I can verify that it's inconsistent. So log verification from a self-certifying root of trust protects against internal inconsistency. All logs must be internally consistent, and anybody can determine that they're not. External inconsistent log comes when I have a purported copy of a log and both logs are internally consistent. They're both verifiable, but the logs themselves are different. So I've got a purported copy that does not match. That means I have a duplicitous log, and duplicity is protected by using duplicity detection. So we need duplicity detection added on to internally consistent logs to protect against external inconsistency. So we're going to talk about those, and we're going to play a game. And before I jump into the game, are there questions that I should be answering? I guess, Alex, there haven't been any questions or nothing
There's
worth.
some questions, but I think we can leave them for the end.
Okay.
I can ask them now if you want. What are you?
Okay. Yeah. If it's about the preliminary stuff, it might be good to answer them now before we get into the duplicity game.
Well, it's more generic, so I think, yeah, up to you.
All right. Well, I don't know what the questions are, so
let me tell you the questions, and then you can decide. Okay.
Okay.
So Dennis is asking two questions. So he's asking, do we have code for KERI? Is it ready to you at the application level? How would the software developer get started?
Okay, that's a good question. Right now, there is a project within the Decentralized Identity Foundation that just started recently. There's a little bit of code there. The goal is to have a working reference implementation of KERI by September of this year. And so we've got some developers that are working on it, but there is no code today. But if you want to help, you're welcome to help. It's an Apache 2 licensed open source project, and we welcome all help we can get.
Awesome. And the other question from Dennis is so KERI does not need a blockchain. So how does KERI help with SSI and establishing a decentralized root of trust without a blockchain? Explain to me, please, how the data persists.
Okay. Well, so the key event logs are what establish the root of trust. So the question, so you have a self-certifying identifier and a key event log. The key event log is ordered with respect to the identifier by the controller. You don't need total ordering with respect to other identifiers to establish the root of trust in KERI. And that's probably the hardest thing to get your mind around if you've been spending the last few years in the blockchain space, because everybody just assumes that you need total ordering, which you do for double spend proofing of cryptocurrency, but you don't need for establishing a hash chain data structure of events on a single identifier. So I just need logs. I just need append-only logs of events to establish the authority, and then I just protect myself against duplicity. And this is what, so that's a good segue to the duplicity game, because I'm protected against internal inconsistency by the structure of the log, because it's a hash chain data structure. The only authority that can sign the log is the controller itself, and that authority is established by virtue of only one controller can be a signer, and the identifier is uniquely attached to the initial keys. So it's a cryptographic root of trust. It's not based on a blockchain. And then the events are all signed by the same controller. And so the question now is, what if the controller produces two different logs? And so we're going to play the duplicity game to answer that question. So Kate's the controller. Kate creates a log of key events that are signed by Kate. And so what is Kate going to do with that log? Kate wants to interact with other entities in private one-to-one interactions. So I want to use this identifier for private one-to-one interactions. So putting it on the blockchain, destroys privacy because I publicized it. But I want to engage in private one-to-one interactions that are secure. So Eve is a validator for Kate. Kate is going to send events to Eve, and Eve's going to validate those and try to establish whether or not Kate is being consistent, because the root of trust is consistent attribution. So if Kate is consistent in all of Kate's statements, then Eve can trust Kate up until the moment that Kate is not consistent, and then Eve can't trust Kate anymore. So Kate's at risk anytime Kate is inconsistent, and she's provably inconsistent if she signs something with a non-reputable signature. And also Kate wants to interact with Joe, and Joe's a validator for Kate. Now, for the interaction, Kate is making a local consistency guarantee. Kate promises to provide a consistent pairwise log with Eve. Says, Eve, I'm going to be consistent. I'm going to give you a log, and I promise to be consistent. And Eve can verify at any point in time whether Kate has been inconsistent just by keeping a copy of the log or the events that Eve has received. So Eve has a log of what Kate sends her. Kate has an internal log. Joe has a log. So Eve uses the identifier A. In this case, it's actually a self-certifying identifier, which would be, 44-byte base 64 random appearing string of characters. But A is what we're representing with compactly. So and then Kate uses a different identifier for Kate's interactions with Joe. So Joe knows Kate by B, and Eve knows Kate by A. Joe can't correlate A and B. Eve and Joe can't correlate to Kate because she's using different identifiers, so she can keep privacy. So how may Kate be duplicitous and not get caught? Remember the difference between internally inconsistent and externally inconsistent. Duplicity is external inconsistency. How can she do that? Well, let's say she sends one version of the log to Eve, and then later sends events that are from a different version of the log with different events that are different from V1 and V2. Can Kate get away with that? Kate can't, as long as Eve keeps copy of V1 of the log. As soon as Kate sends events from V2 which are different, Eve can detect them and says, Kate, you're being duplicitous. I can't trust you anymore. At this point, whatever value A had to Kate has been destroyed, and Kate did it to herself. Kate destroyed the value in her identifier. So Eve is perfectly protected in this case. There's no way that Kate can be duplicitous and not get caught as long as Eve keeps a copy of the log. If Eve loses the copy of the log and Kate sends a new copy of the log, then Eve won't know that Kate was being duplicitous, but if the new log is internally consistent, that Eve might be fine with that, because for whatever reason, Eve didn't care about keeping the log, so Eve doesn't care about maintaining consistency over time. Likewise, Kate could use the same identifier with Joe and a different version of the log with different events. But all Kate has made is a local consistency guarantee. So Kate is not duplicitous in using the same identifier but a different set of events with Joe, because she hasn't promised either Eve or Joe that she's going to be consistent globally. She's only going to be consistent to them individually. And as long as she only uses V2 with Joe and only uses V1 with Eve, she's still not duplicitous, because based on her promise, and everybody's fine. So let's say that now that Kate doesn't like talking directly to Eve and Joe. Kate likes to be offline, and so Kate wants to have high availability, but still private one-to-one interactions. So Kate creates a service or an agent that Kate controls that holds Kate's log. And then Eve can talk to the service, and Joe can talk to the service, and the service has high availability, so both of them, so Kate can go away. So how does this change? Well, it changes now is that the service now is a point of vulnerability. Kate needs to make sure that the service is consistent and not duplicitous, but the guarantee is still the same, a local consistency guarantee. So, you know, how may Kate /server/agent be duplicitous, not get caught? It's the same guarantee. You can use different identifiers. If they use a different log, Eve can detect that Kate's being duplicitous by virtue of a different log. If Kate truncates the log, then Eve it won't match their log. I mean, if the service deletes the log, Eve won't see the log at all, which only hurts Kate, right? Because Kate can't talk to Eve without the log. Eve says there's no log, so I guess there's no interaction. So all the things that the service can do to hurt Kate, but they don't hurt Eve. It makes Kate unable to talk to Eve, but it doesn't hurt Eve. And that's the important point. If I'm only making a local consistency guarantee, the only person that's hurt by that is Kate, not Eve or Joe. So now it gets really interesting when we want to change from a locally consistent to globally consistent. So in this case, I've got Kate talking to both Eve and Joe using the same identifier, highly available, public one to any, because she's using the same identifier and she's making the promise that she's going to be globally consistent, that anyone that Kate talks to using identifier A will get the same log. That's the global consistency guarantee. So that brings up a different question, and that's where duplicity comes in. So if I break the promise of global consistency, it's provable. And how is it provable? Because anytime that I send events to one person and sign them, and send inconsistent events either to the same person or a distant person and sign them, then all they have to do is compare events to prove that I was duplicitous. So the Kate is always at risk of being found out if she ever acts duplicitous, even once, right? Forever, because that signature that she signed, that inconsistent event, is non-reputable, and which means they can reproduce it at any point in time and say, hey, 10 years ago, you did this. So how may Kate be duplicitous and not get caught? So what are the exploits that Kate can employ? Well, she can send two different versions of logs to Joe and Eve. And so she hasn't got caught, but if she can truncate the log, so Joe has a different version of the log that Eve has. She can delete the log so Joe doesn't even get a log. These are all things that Kate can do. These are just hurting Kate for the most part. But let's say that Joe and Eve need to interact so that they both can know that they're read consistently by Kate. Well, if she has sent different logs to Eve and Joe and they interact and compare notes, they will know right away that Kate is duplicitous. So the only way Kate can be duplicitous and guarantee she does not get caught is to prevent Joe and Eve from ever talking to each other, which is possible. Kate could control them such that Joe and Eve can never talk to each other. But if Joe and Eve need to interact, then it defeats us, because that by being isolated, the interaction fails, right? So in that case, if global consistency only matters after they need to interact, then all Kate's duplicity does is prevent the interaction from completing. But let's say that that's not a problem. Let's say that they don't necessarily need to interact, but sometime in the future they need to interact, and they want to be protected against that. One way to protect it for them, and this is what KERI uses, is that I can have another entity, Doug, and Doug's a global duplicity log. He has a copy, and Eve sends a copy of the events that Eve gets to Doug, and Joe sends a copy of the events Joe gets to Doug, and then Doug says, oh, that event you sent me is duplicitous, so you can't trust Kate. And so as long as Doug exists, Kate will always get caught. And in fact, Doug can even make it harder for Kate to not get caught by interacting directly with the service and changing the identifier that Doug uses to interact or get from the service, or be anonymously reading from the service, so that Doug always has a good copy, and anybody that cares about Kate can check with Doug and know that Doug is that Kate hasn't been duplicitous so far. So as long as I have a way of detecting duplicity, both Eve and Joe are always protected. Doug serves the same purpose as a blockchain, but doesn't have to be a blockchain. He just has to have a copy of the log. That's all he has to have. It's the minimal amount of infrastructure that you need to ensure that Kate is caught if she tries to be duplicitous. So if there are enough Dougs out there, or enough infrastructure that is providing copies of duplicity logs, then you get what's called ambient duplicity detection, which means you can detect duplicity anytime by anybody, anywhere. And there's actually something that's very similar to this that is used right now, and it's called certificate transparency. So there's references for that, but the DNS system, unfortunately, doesn't have a strong root of trust. But if you use the certificate transparency, you basically have a global duplicity log or inconsistent log that allows you to detect if somebody is using certificates in an inconsistent way. And so KERI takes advantage of that same idea and adds that onto a cryptographic root of trust with strong bindings to get an inviolable security guarantee based on both internal consistency from a cryptographic root of trust and external consistency using ambient duplicity detection. So that's why KERI works. So let's think about what that means. KERI enables a cryptographic proof of control authority, provenance, for each identifier. The provenance comes from the log. The proof is in the form of the key event receipt log. The key event receipt log is end-verifiable. Anybody that wants to read the log can verify it. It isn't dependent on trusting anything. You don't have to trust anybody. It's zero trust. The end user alone may verify. There's zero trust in any intervening infrastructure. Curls may be ambient verifiable, right? Which is you have a global verifiability, right? Anyone can verify the log anywhere at any time. The result is that you have this thing that has these features. You have a self-certifying root of trust, ambient verifiability via certificate transparency. There's a couple of other algorithms, KERI, which allows recovery, and post-quantum security because of something called pre-rotation, which we can talk about in a minute. For those of you that are familiar with DIDs, what does KERI mean? Well, KERI provides the equivalent of DID key if I use a non-transferable ephemeral self-certifying identifier. It provides the equivalent of DID peer if I'm doing direct mode one-to-one private conversations, and the equivalent of public identifiers like DID solve if I'm using the indirect mode one-to-any. So it basically does everything in one identifier system. And so we're building something called DID uni or DID un, which is the universal DID method to be compatible with the DID spec. So that's a good point to pause to answer questions.
Yeah, awesome. Yeah, Dennis had a couple of questions, so he's just let me find them here. So he's asking, is it validator a new role artifact that you have introduced into the KERI architecture?
Well, a validator is anybody that wants to establish control authority for the identifier created by the controller of the identifier.
Okay.
So it's a generic term, but from a code perspective, yeah, a validator does certain things. They verify the log, they apply any other, they apply duplicity detection, or they leverage somebody that is duplicity detection, and whatever other logic they want to apply to say that, yeah, these events I can trust.
Great. So we have this other question from Dennis. He's asking, going back to the triangle that you had with Kate, how do we verify the integrity of Doug?
Well, Doug can't do anything because he can't sign anything. So the worst that Doug can do is delete a log. So if I have an ambient service that provides multiple redundant copies, then I can check that, I can check that at least one of them hasn't deleted their copy. And if there is no copy, if none of them have a copy, and the only copy is the copy I have, then by definition, there's no duplicity because Kate's only produced one copy. There are obviously race conditions where Kate produces two copies, Doug doesn't have a copy yet, you verify your copy, and then the second copy shows up. But those are no different than the same things that happen with any blockchain, right? You take any blockchain, and if I can isolate you from the network so you can only talk to one node on Bitcoin, then that node can provide you with a forked, Bitcoin chain that has invalid transactions in it. And the only way you can know that is talk to other Bitcoin nodes. And so there are some people that have random Bitcoin, randomize their Bitcoin node access to guarantee that they're not isolated from the network. So Doug is doing the same sort of thing. So you can make Doug as reliable as you want it to be, because all Doug is doing is providing redundant copies of logs. It doesn't have to do distributed consensus in the sense of total ordering. So it's IPFS. Doug could be IPFS for all intents and purposes. For those of you familiar with the interplanetary file system, you could say, we're just going to put everything in IPFS and check it. Make sure that the copy that I have is the same copy that's in IPFS. And if it's not, then I know they've been duplicitous. And at that point, I don't care which one is the valid copy because they've been duplicitous. So I can't trust them from that point on. The first event at which they're duplicitous is the event at which I can't trust them.
Okay, another question from Dennis. He's asking, does the size of the log impede performance? It is in the end verifiable, so do you just need the end part of the log for verification?
For duplicity, yes, the last one, because it's hash chained. So if you have an event that doesn't match your latest event or doesn't hash chain back to your latest event, then you know that their log from your log. And you could also do a Merkle tree of the events in your log, and then verify any event in your Merkle tree in the log without having to keep a copy of the log. You just have to keep a copy of the Merkle tree of the log.
Okay. And Lucas, last question that we have outstanding here, he's asking, do I need to show the full log to anyone I transact with, even though I just want to show a part of my log, example, a credential from another interaction?
Yes, because they can't verify the root of trust. So they have to have access to a full log at some point in time so that they can verify to the root of trust. Once they verify to the root of trust once, they don't actually have to keep a copy of the log. Does that make sense? They just need to keep the last event that they've seen, and any events since then, they just need to verify as they go. But if they don't at least verify the root of trust, then they're trusting, you know, in something that they haven't ever verified. But you can certainly cache the fact that you've verified sometime in the past, and now you just have to make sure that all events chain back to the last event that you verified. So you're basically just verifying as you go and then just keeping the last event.
Great. No more questions, Sam.
Great. Well, we've got like 3 minutes left, and I don't know how much interest there is in me in going into more detail on the, like, let's say the in the pre-rotation and the key management screens, it's a little more detailed, but I can give a brief overview, and this might be helpful to people who understand key management. So we can cover just the basis of pre-rotation if there aren't any more questions. So we've talked about inception events, rotation events. In KERI uses something called pre-rotation. What this looks like is that in the inception event, you have the initial public key, and this is simplified to a single key instead of multi-signature, but all of this works for multi-signature. So instead of a single key, you'd have a set of keys. But I have this initial set of keys, and then in the inception event, I declare the next key and make a cryptographic commitment to it where I have a digest of that next key. So the next key isn't there, just a digest of it. So I've created 2 key pairs, the initial one, public key, and the second one, which is the next one. But this private key of the next one is not exposed at this point. So you could create it in your coal mine down at the bottom, you know, air gapped. You create this key pair, and the private key you keep down in the coal mine. You bring the key, create a hash of it, and then you bring the hash out of the coal mine and stick the hash in this event. You sign this event with the initial private key. So the private key has been exposed by the signature, but the next key isn't. And this is post-quantum secure because hashes, if they're strong enough, aren't any weaker than, aren't weakened by quantum computers. So now even if somebody has a surprise attack, they can invert your next key, so you can always recover your control authority by doing a rotation event to the unexposed next key. So that's what pre-rotation is. It's a pre-commitment to the next key. You've pre-rotated your key, and this is your next key is your next rotation key. So when I do a rotation event, I go extract my private key buried at the bottom of the coal mine. I create a rotation event. I expose that key. They can verify that the hash of that key was in this event. So there's no way for an exploiter to create an alternative rotation event because I forward chained, right? So it's not just back chain, forward chained my rotation event by the next key. So I'm protected both forward and backward cryptographically. So now I expose this key, I sign with this one, but I also make a forward commitment to the next key, which is still at the bottom of my coal mine. And so now with pre-rotation, I don't need to have multiple layers of key. I just have a single sequence of keys that is both back and forward chain to preserve my control authority. So that's the simplest infrastructure for key management that allows me to rotate keys in a best practices cryptographically secure way. So this just shows you a sequence, and you can see the keys. The underbar means it's a hash. All right, so I have C0, C1, the current key signature was C0, rotation, I've rotated to C1, I pre-declare C2, or commit to C2, I sign with C1, and so on. And then I can, use this in various ways. But I think we've run out of time. So happy to answer. Yes.
You don't really have to worry about the time unless you have to go. Then it's okay. But
yeah, if people want to hang on, I'm happy to go for a little bit longer.
I think I'm getting a lot of positive feedback. I mean, Jefferson is saying awesome stuff. Drummond, I mean, you know him. He's saying, he's asking a question actually. So he's saying, forward chaining is, in my honest opinion, extraordinarily powerful. Why hasn't anyone done this before?
Well, I first wrote about it in 2018, so it's been public knowledge for at least 2 years. So I guess people just don't read. That's why.
Yeah, and Mark, he's saying great stuff too. And I mean, just one more coming in. I think, I mean, if you're okay with your time,
Oh yeah, I'm happy to go on. Yes, this would be.
I would suggest just keep on going. We still have 18 people in the room.
Okay.
Saying
yeah, when it gets down to a couple, then I'll
then we stop tomorrow. Yeah.
Yeah.
Okay. So Dennis is asking, is the entire project on the diff website a KERI project?
Yes, KERI. So
Okay.
there's the KERI repo has the documentation. The KERI Py repo has the Python implementation. There's a KERI JS repo for the JavaScript, and there's a KERI aux repo for the Rust implementation. So far, the only code that's on there is the Python stuff that I've written, but there is a pull request for some JavaScript stuff, and I know somebody has volunteered to work on a Rust one, but hasn't submitted a pull request yet. And that's probably because there isn't enough Python code to go on yet for somebody to get really serious about the other implementations without, a lot of stepping on toes and doing stuff, because it's really early. We just really started at IAW last month, and so we're starting to ramp up.
Okay. Then Mark, he's also asking, is KERI collaborating with the newly launched Trust over IP Foundation?
Yeah, I not in any formal sense, but I'm talking to everybody in there, and there's no reason that KERI wouldn't be part of that.
Okay,
I mean,
that's all I have over here right now.
Yeah, I know, Drummond, you're trust over IP. You can answer that question better.
Yeah, and Drummond, he's saying, yeah, KERI is very welcome to trust over IP, as you could have imagined. So, okay, so I think if you want to just keep on taking it forward here until you finish. I mean, we still have 17 people in the room, so up to you.
Yeah, no, great. This is great. So one of the things that KERI does is it changes the conversation about security from a conversation about the security of infrastructure to a conversation about the security of your key management and your key management infrastructure. So most people, when they think security, they think, oh, blockchain. How secure is my blockchain? Is it permissioned or permissionless? How hard is it to get a 51% attack, et cetera, et cetera? None of that matters for KERI. KERI is all about, are your private keys private? And if your private keys are private, then the only exploits are brute force attacks against the public keys. And because the next public keys are actually protected by a hash, you can't even you have to brute force attack a hash algorithm, which is post-quantum secure. So that is a very, very, very high level security. And now your exploits are limited to exploiting your private keys, which if you're, so now private key management and protection is the root of your security. So if I think about key infrastructure, not blockchain infrastructure, not administrative infrastructure, not server infrastructure, but my key infrastructure, the term valence to talk about how multifaceted my key infrastructure is. So the simplest key infrastructure is a univalent infrastructure. And so what I have is a key pair generation infrastructure. So I might be generating key pairs like the example I gave in the bottom of a coal mine using an air gap, whatever, handwritten on paper, engraved into platinum bars, infrastructure. Or it might be the secure enclave on my iPhone, or the equivalent on or some trusted execution environment, or some trusted platform module that is generating my key pairs. And then I have a key event signing infrastructure. And so in the signing infrastructure, I have to take my private key, put it in this infrastructure so that it can be used to sign things. So the signing infrastructure might be just some software running on my server or my agent, or it might be a TPM or a trusted execution environment or something more sophisticated. I get to choose how I want to manage that. KERI doesn't care, because KERI says you get to pick. And if you care about your security, then you pick well appropriate to what you're going to use your keys for, what your identifier is being used for. If your identifier is being used in an IoT application where all you're doing is streaming temperature measurements from some thermostat mounted on a wall in a building, right? Maybe you don't need to use a TPM for your key management. You're happy to just store your private keys in memory on your 32-bit Cortex M4 Cortex processor. If you're running a back-end data-driven application services, just storing your private keys in a root permission protected file may be good enough. If you're doing financial transactions, probably not. Probably want to have them in a secure enclave with some better protections. But an infrastructure just means that I've got one key pair place and one key event signing place. And so all of my KERI events basically just go from, I create two key pairs, I expose the public and private key in the key event signing infrastructure. I publicize the public key in the events. The private key stays in my infrastructure, and I publicize the next key as in a hash, because I've got to hash it. So the public key goes to my key event where I hash it, but the private key never leaves my key pair generation infrastructure till I need to use it. So as long as my key pair generation infrastructure stays secure, then I'm fully secure. I can always recover my control authority by rotating, even if my private key for my current signing gets compromised. So a bivalent infrastructure says, well, you know what? I want to have different degrees of security and different degrees of performance and scalability for my signing. And so I want to segregate my root control authority from a lesser control authority for signing in high volumes. So in this case, I have a delegator, which is my root control authority, that is using my coal mine for my key pair generation. And my delegate is just some server someplace that's going to be signing web page interactions or data-driven, processing of whatever I'm doing. And so I don't need that to be as secure. And because these are delegated, and we haven't talked about delegation and KERI, I can always revoke these keys and recover them with this guy. So I now have two layers of infrastructure, a highly secure infrastructure that controls a more scalable, secure infrastructure. And then I can go to a multivalent, so I can get horizontally scalability, where I have one delegator infrastructure that's controlling multiple delegate infrastructures, and each delegate infrastructure may have its own security guarantees and its own key management policies. But they're all using the pre-rotation scheme. They're all using the same events. They're all using the same self-certifiers, the set of derivations that we've generated. So it's all one code base to do all of these different infrastructures. So you can go from very simple one user systems to enterprise level scaled out key management infrastructure, all using the same KERI code base. So what KERI is doing in the single univalent thing is that I can repurpose keys. So another way of thinking about it is I have a set of signing keys that have been used once to rotate, and now I use those keys over and over again to sign. If at some point I'm worried about these keys being compromised, then I do a rotation to a new thing, and so now I'm protected. I can always rotate away from an attack in that case. Or in KERI, if I don't like that exposure and I want to be even more secure, then what I do is my payload of anchors, instead of putting them in separate interaction events, which give me some performance advantages, I put them in actually put them in the rotation event. So now each key is only used once. It's a one-time use key. So I use a key, I use it to rotate and to sign a payload, and then I can't use it anymore. And so this is if your tinfoil hat is 3 or 4 inches thick, you're going to be doing this. I guess that's a duplicate slide. Anyway, interaction delegation. So let's talk about delegation. Are there any questions on pre-rotation before I go to delegation?
Yeah, let me share the comments we have. It's a little bit mixed up. So, I mean, just a general comment from Mark. He's saying blockchain as a term has come to carry a lot of baggage, unfortunately. So I think this just refers to your previous comment. Then we have Dennis. He's saying, does the public-private key format matter?
No, because the derivation code allows you to use whichever format you want. So anybody that sees an identifier looks at the first byte or two. Right now, all the formats that are reasonable use, that are elliptic curve formats, are 32-byte keys, which when you base 64 them, there's one pad byte, and so in KERI we prepend the pad byte, replace the pad byte with the derivation code byte. So it's very much like a multi-codec type approach. You look at the identifier, you look at the first byte, it tells you whether it's an EC DSA or an ED25519 or whatever other type of key format you want to use. And then when you rotate keys, you can always rotate to a different format.
Great. And Dennis is also asking, for instance, could KERI support BIP32 key structure? So, and with BIP32, he says, I mean, the hierarchical deterministic key creation and transfer protocol BIP32, which allows creating child keys from parent keys in a hierarchy.
Yes, you could use that in your key derivation if you chose. KERI would not know that. KERI, but if you chose to organize your keys across your different identifiers that way, you certainly could. And I know some people that are doing that with in their architecture designs for things with KERI, where they're just saying, yeah, we're gonna use a BIP32 like derivation scheme for all of the keys, but KERI is agnostic about that.
Cool. Artyom is asking, it's not that clear how root of trust, say rotation event, could be multi-sig. I mean, N of T.
Yes, so I haven't given you the full, that's further down in the thing, but because I'm using simplified versions of the key events, so I'll exit out of this and we'll go down, and here is a full event format. So what you have actually is in the full key config, it's not just the public key, it's actually a threshold. So your K of N, you'd put, and then the public keys is a list. So now you know the N from the number of keys in the list. So your K of N is provided this way. And there's also actually in KERI a weighted key scheme, which, yeah. So your threshold actually could be a list of lists of weights, of threshold weights. So you could do relatively any arbitrarily complex logic threshold operation using this scheme in KERI. And it would take a while to explain how that works, but I anticipated people being able to want to do, like, I need 2 of these signatures and 3 of these signatures and 1 of these signatures. And that's what this shows here. So I hope that answers the question.
Yeah, he's saying thanks. That's great. Yeah.
Okay, so let me go back to where we were. Here we go, delegation. All right, so any more questions?
That's it.
Okay, so delegation, how does delegation work? There's 2 ways to, whoops, I hit the wrong button, sorry. There are 2 ways to delegate and KERI. One is using interaction events and the other is using rotation events. Interaction events are going to be a little more scalable. Rotation events are not going to scale performance as wide because you're using a lot more keys, but they're more secure. It just depends on what sort of application you're using. I anticipate most people are going to use interaction events to delegation. Payload in your delegator, the payload in an interaction event is actually an inception event for a delegated identifier. The delegated identifier has, and you have a seal or an anchor, either cross-anchored, is an inception event that is declared as a delegated inception event. And then this key log can do interactions, and at some point, if the delegator says, okay, I need to rotate keys for this guy because I think they've been compromised or I've detected a compromise. So they do a new interaction event that is a delegated rotation, rotates these keys, and then he keeps going. Anybody verifying, and so on, right? And if you want to revoke keys, you can. You just do a rotation that rotates to a null key, and then you've revoked the delegate key event. Anybody wanting to verify this can just go to this key log, verify up to this point, use the anchor to go back to here, verify up to the root of trust. And this can be done, and then here's all of the associated information in the events, right? So here's the delegating inception event, here's the delegation anchor, the digest here is the digest of this data, which is the delegation data. There's a delegation seal in the delegated event right here that points back to the delegating event. So this digest is of this event. And then here's the delegated data that came from this data right here. It's essentially the same data. And so they're cross-linked delegated events that are verifiable and verifiable to anybody that gets a copy of the delegate event stream and then can look it up and verify it. And then this, of course, and then there's the interaction event data. And the delegated interaction event looks no different than a interaction event because it doesn't rotate keys or do anything special, but it can delegate other key event streams. So you can have something like this where I've got one master delegator and a bunch of minion delegated streams. And each of these streams could also delegate streams. So I can have an arbitrary tree of delegated identifiers using just the same set of KERI events because they're recursively applicable in this case. And then, like I said, if your tinfoil hat is thicker, then you can only use rotation events for delegation. And in this case, you can't do an arbitrary. You can do a one-level tree, but you can't do all the way down because these don't have authority to rotate themselves or to rotate in a rotation event because the rotation event is pointing back to the delegator. Although a future version of KERI could allow that, but I don't know that there's a strong need for that. So in KERI, a live exploit of the current signing keys is protected by a rotation. You just rotate and you're protected. You recovered control authority. So pre-rotation provides protections from successful live exploit of the current signing keys. A dead exploit is that you have stale next signing keys that have been exposed in the past, and somebody wants to create a delayed event history. And because the keys are exposed, they may be able to exploit that and compromise them. So they can generate, whoops, what did I do? Okay, they may be able to generate an alternate event history, but the key is the alternate event history must be delayed because they can't invert the next keys. They have to compromise them after they've been exposed, which means that your duplicity detection your original copy will be first, and so you will be protected against dead exploit. Because the worst case, the dead exploit is just going to say, oh, you've been duplicitous, so you can't trust it anymore. But as long as you have an original copy, you know which copy to trust. And if you have Doug, which is your global duplicity detector, Doug will only have one original copy, because any copies, he will say, well, this came later, and so it must be duplicitous, and then you can decide whether you want to trust the original or not, and the validator gets to make that decision. It's not up to the controller to make that decision, it's up to the validator. So the validator can protect themselves by using duplicity detection. And a live exploit of the next signing keys is practically impossible because it requires you to invert a digest and do a brute force inversion of the next digest and the underlying public key. And if you can do that, then no key management scheme on the planet is secure. And so I'm not worried about that. Now, if someone can do a side channel attack against your private key store because you happen to publicize your private key core, then yeah, then anybody can exploit you and you're not protected at all. But understand, protection is solely based on key management now, not any other thing. And so that changes the whole discussion about identity. It's truly decentralized. It's just, do you manage your private keys? Then you can have decentralized identity. You don't have to have anything else. I mean, anything in the sense of something heavyweight like a bunch of blockchains. You just need key event logs, which anybody can stand up and spin up for duplicity detection. So there are two operational modes, a direct event replay mode. So when we did the duplicity game, I mentioned these two modes in passing. So this is just going into more detail. And where are we at? Yeah. So we got time. It looks like we still got 11 people left. Wow. Okay. Pre-rotation knocked off half the people. So there we go. So direct mode, A to B. So what does entity A have? They have an event generator. They have their own copy of their key event log. They have identifier A. They send key events to B. B is validating those events to know whether they can trust A. So they have an event validation. They respond to events by acknowledging them and signing them. So now A has a signed copy that B saw and acknowledged the event. So not only is A providing proof of its events, but A now has proof that B saw an event in order. So B can't later say, oh, I didn't know about that event, because A can say, no, I have the event, and here's your signature. So you acknowledged it, I know that you have the event. You know, you can't lie about, you can't be duplicitous about not seeing the event. You saw it. So they're both protected. And then likewise, B's identifier to A has the mirror image where B generates events for B's identifier. A validates those, sends back a receipt that B keeps track of. Now both of them are mutually protected in a private pairwise, one-to-one interaction. And A can have any number of those one-to-one interactions with any number of other entities, with using any number of identifiers without deference to anything else. No, they don't need anything else on the planet to be able to have private, secure, one-to-one interactions ad nauseum, right? Completely, totally decentralized. All they have to do is standardize on the event sequence and do their validation. But if I want to have availability so that I'm not directly talking, then that's indirect mode. And so in indirect mode, A creates an event promulgation service. The event promulgation service consists of witnesses who witness what A does. So these are controlled by A, designated by the controller. These are agents or servers that have copies of A's events, and they sign those events. So the first one they see, the first valid verified event they see, they sign and add to their log, respond to A with a signature, a signed version, a receipt. A now has a copy that the first witness witnessed it, has a copy. When A then sends that event to the next witness, A can also send a receipt from the first witness saying, not only here's the event with my signature, but here's the signature of this other witness. So now this witness has A's and this witness's signature. So this witness knows that this witness can't be duplicitous. And then he can talk to all of them. And then when he gets to this last witness, A will have a fully witnessed event log with signatures from all the witnesses, and then he can just send those copies of that, or broadcast or gossip copies of that to the other witnesses, so that at the end of 2 rounds of talking to the witnesses, every witness has a fully signed, fully receipted copy of the event. And now anybody can detect not only if A has been duplicitous, but if any witness has been duplicitous, because once the witness signs it, they have gone on record as saying, this is the event that I've seen. So identifier validator over here just needs to query any one of these to get a fully witnessed, fully signed event log, and know that they now have a proof, they now can prove duplicity at any point in the future, as long as they keep a copy. And these witnesses now provide high availability because, if one of the witnesses fails, A just goes to one of the other witnesses. If there's a load balancer or something like that, A can always get a fully receipted copy, high availability. And as long as A trusts controller to not be duplicitous, A doesn't have to trust the witnesses, because the witnesses are mutually signing stuff, and if controller didn't sign it, then the witness can't sign it because they can't verify it. So it's all the way through. So that's the basic system, but validator may not trust controller A. A may be malicious. A may say, you know what, I'm going to create a duplicitous copy of my event log. And since I control the witnesses, they're going to provide 2 different copies. So A then adds watchers, and watchers are designated by the validator, and the watchers basically have copies. And then now I've got a high availability key confirmation service. This is my duplicity detection. This is Doug, right? So I can spin up some servers that are my Doug, and if controller A ever generates an event that is duplicitous, and any one of these guys read it, then A will be able to detect it. And if these happen to be global or public watchers shared by other people, then A can do duplicity detection against the events for the same identifier against other validators. So this looks like this, where you have watchers and jurors, which are doing the duplicity detection. A judge is looking at watchers and jurors and making a decision. And so entity B just says, hey, I got this service that I just talked to, that I control, that protects me from whatever A does. And this looks more complicated, but understand, these guys are just sharing sheets. They're not doing any complicated proof of work or proof of stake or PBFT algorithm. They're just broadcasting receipts to each other. So it's inherently scalable. You can run a serverless architecture, a market service architecture, do tens of thousands of transactions per second, and not skip a beat with this kind of an infrastructure. And if you really have a reason why you need to use a blockchain, which there are really good reasons to use a blockchain, you can actually do it this way. You can basically say, my ledger, the blockchain ledger is going to be the witness, and I'm going to have an oracle. Sorry, the oracle on a ledger is my witness. And if B, the validator, trusts the ledger, then B just spins up an oracle name ledger to be the B's watcher, and now you just using a blockchain as an immutable data store to provide your event log. But I can change out this ledger at will. I just do a rotation event in the rotation event, I specify a ledger or a different, because I can specify a witness set every rotation, and so I can move from ledger to ledger at will. The controller can, and I'm good to go. I'm portable. So that's the thing that KERI does, is that it indirects the whole idea of security to an end-verifiable event log, and any immutable data store can provide the immutable data store service. And if I want to use a ledger for that, ledgers are really good immutable data stores. They're expensive and slow, but they do immutable data stores really, really well. And so if I have other reasons to use a ledger, I can continue to use a ledger, but I'm not locked to that ledger. And that's the key difference with KERI. So what KERI does is it introduces the idea of separation of control. So a shared permission ledger has shared control over shared data. So shared data is good. The shared data is the key event log. The shared control is bad because, well, I got to get people to agree, to permission, to work together, to do whatever they do to make sure that shared control works. And that's a lot of work. That's bad, relatively speaking. So shared control between controller and validator may be problematic because the controller may not and the validator may not trust each other, right? And so that introduces governance, scalability, and performance issues when I have shared. That's what ledgers are. They're shared control over shared data. But KERI allows you to separate the control so that you can have separated control, but over shared data. The shared data is the log, but the separated control is the promulgation service and the confirmation service, or my witnesses and my watchers. So now that I have separated control between the controller and validator, I have better decentralization because it's more decentralized by definition. There's more loci of control, and so that's what I mean by decentralization, not distribution. More flexibility, better scalability, lower cost, higher performance, and more privacy at comparable levels of security because I've designed the security right. So that's the end of the presentation without going into the really, really deep details. So questions?
Great. Maybe go to the last slide, and meanwhile, well, we can see. Let's see what based on the
questions.
the
very last one.
So Dennis is asking, Sam, what is the timeline for getting some code in a better state?
Well, our goal is to have a working reference implementation by IIW fall. So, between now and then, it should be working. Hopefully, in 2 months, which is halfway, we should have something that you could actually play around with. That's basically working, just not not fully featured. I've already got some of what's been happening the last 3 weeks has been just nailing down the serialization stuff, and that seems to be nailed down. So there really isn't anything right now that's stopping development. I think all of the sort of architectural questions and standard approaches have been answered, which the serialization and a couple of other things were things that were open questions as of IAW a month ago. And so those have been nailed down. But you know what? If you want it to go faster, come help.
Yeah, we encourage everyone to do that. There's another question from Dennis here. Is the witnessing signing back propagating back to the previous witnesses in the chain?
No. The chain is completely generated by the controller. The controller is the only source of truth. All the witnesses are doing are receiving that. They're confirming that they saw that. And once they confirm, they've made a commitment that is the authoritative event from their perspective. So the first event they see that they validate against their copy of the chain is the only one they will ever sign against. So that provides a very important security guarantee because there's a concept in KERI called the threshold of accountable duplicity, which allows us to recover from a key compromise. And once I reach the threshold of witnesses that have signed a version of the log, they can't go back because they signed it. And so when I get a majority, then I can make the same sort of guarantees that I make with any distributed consensus algorithm that says if I have, 3 F plus 1, where F is the number of potentially failing witnesses, if 2F plus 1 sign, then there can only be either one authoritative copy of the log or none. There can't ever be two, which means that the validator is protected because I basically have neutralized any other possible copy, right? So I get the same guarantee. It's the same guarantee that I get with any PBFT algorithm. I just don't need to have a three-phase commit because there's only one source of truth, and that's the controller. So I take advantage of a single source of truth, and I only need to order events with respect to identifier to greatly simplify the whole idea of distributed consensus. But I'm still using the same guarantees in the sense that if I get a majority of witnesses witness, then it's immutable. It can't go backwards. I've neutralized any other copy. So it's every bit as secure as any PBFT algorithm. And that's a very strong statement, but I'm pretty confident in that statement.
Wonderful. Let me just comment that Sam is working together with Drummond Reed on the chapter for decentralized key management, which incorporates a lot of this thinking. So it's part of the self-sovereign identity book that we've been working on for ages now, and that we will continue working on for ages. But you can acquire like the first, I think like you have 10 chapters published now on the website here, which is with Manning on self-sovereign identity book. And I hope that hopefully in the next 30 to 60 days, also the decentralized key management chapter will come out, because Drummond and Sam are working on that, just for everyone else's benefit. If there are any questions, please bring up your questions. If not, Sam, any final thoughts from your side?
Yeah, just if you have more questions, go read the white paper, look through the slides. There's more detailed slides that we didn't get to, that if you really want to get down into the weeds, it's all there. And I welcome feedback. And if you find something that I missed or isn't clear, I'd love that kind of feedback, because it teaches me, helps me to improve how I message out the KERI stuff. I'd like to see some momentum build, because I think this solves the fundamental problem of being able to actually secure the internet with truly decentralized identity.
Wonderful. That sounds very promising. For everyone else, if you want to keep on learning and hearing about the next SSI meetups, please sign up to our newsletter. Just go to our website, ssimeetup.org. There you can sign up. That's the quickest way. You also have our Telegram channel and all the other social media like Facebook, Twitter, etc. And our next session will be with Tim Bomer, who's Mr. Identity in Canada, and he will be talking about the Pan-Canadian Trust Framework that he has been working on together with Dave Roberts. They've written a chapter also in the SSI book that has been published already, that is available on the website. But they during that session, they will do like a full talk through the Pan-Canadian Trust Framework and how SSI helps making digital identity work for governments too. And they're both high-profile identity experts in the Canadian government. So really encourage you to go there if you're interested in trust frameworks, governance frameworks, and some of the more legal and structural aspects of these kind of things. And without further stuff to deal with, Sam, thank you so much for joining us today. I think this was really interesting. It was one of the more technical sessions, but there were a lot of questions, so that's really good. And I hope to have you back in the future too, when you feel like, so that we can keep on digging into the details about how you're making progress with this.
Yeah, great. That sounds so. Should I just stop screen sharing now? Is that what I should do?
You can do that. I'm just gonna stop the recording, and we're gonna say goodbye to everyone.